Hello, this is Jennifer Martinez, and in this video we're going to discover exponential functions. We're going to do this before we start with our notebook, but then we'll get right back to our notebook. So first, what is an exponential function? An exponential function is a function that describes quantities that grow at a constant factor. In Chapter 2, we talked about linear functions. Linear functions describe quantities that grow at a constant rate. What's the difference? Well, when something grows at a constant rate, say something is growing by $2 a day, that means you would add $2 every day to your previous amount. When something's growing by a constant factor, you're going to multiply. So for instance, if something is growing by a constant factor of $2, you would multiply $2 every day to your previous amount. So that's the difference, which is why I picked this example. If you took $1 on the first day of the month and doubled it every day for that month, all 30 days, how much would you end up with at the end of the month? So I'm going to start with defining some variables. I'm going to let x be the number of days, up to 30, and let y be the amount in dollars in the bank. And let's just make a chart to see what happens. So on day 0, we're going to start with $1. The first day we're going to double. We're going to double every day. So that would be $2. The second day we're going to double again. Times 2 would be 4. Third day, double again, 8. Think that no big deal. Fourth day, be 16. And I'm going to try to come up with the equation here. So I'm going to just call this 2 times 2 times 2, and then I'm going to multiply this by another 2. I'm going to multiply this by another 2. So this is like 2 to the 4th. 2 cubed, 2 squared. So that way when I do 5, notice how, which by the way is 32, I just know it's times 2 to the 5th. It's going to help me with the formula because you can see a pattern here. If you want to know a formula between these, we're going to have, it looks like 2 to the x. Let's rewrite that. That looks nicer. So we have $32 by the end of 5 days. No big deal. So and you can see here, it does make sense. So if we picked a 6, you know it's equal to 2 to the 6. And if you take 2 to the 6 on your calculator, it is 64. So that is the function, and it wants to know how much will we end up at the end of the month, at the end of the 30 days. Well, I don't feel like doing this for 30 times, so now I have my formula. I can just plug in a 30 and see what happens. But before we plug in a 30, I'm just going to plug in a 10 just so we get used to this a little bit. What happens when you plug in a 10? So I'm going to take 2 to the 10 on my calculator. Let's do it like this, 2 to the 10 there. What would that be? We've made $1,000. Pretty good. I'm just curious about 20 before we get to 30. Let's just do this a couple more times. After 20 days, we're going to be a millionaire. So you can see here an exponential function starts off slow, but then it rapidly expands because right here, say at the 10 mark, now we're going to be making $1,000 every day. At the 20 mark, now we're going to make $1 million every day. So we're going to multiply that by 2. So drum roll, what happens when you put in a 30? 2 to the 30th. You can try it on your calculator. See what you get. By the way, this is going to be, we're going to end up, put that in dollars, a billionaire. right? There's 1,000, a million, so there's a billion. So you can see where doubling every day expands a lot more than linear function, which what would you have if this was linear? If this was linear, you would still end up with 0, 1, but you would add 2, add 2, add 2 to give you, what would that be? Actually, I think we start with 1, so it would be 2x plus 1. At the end of the 30 days, you would end up with 2 times 30 plus 1, which would be $61. So you can see it grows a lot more rapidly, an exponential function, than a linear function. So now let's start with our notebook. On page 94. Example 1. In a population of bacteria, there's initially 5 million bacteria. Fill in the table and write a formula for f of t, the number of bacteria in millions after t hours for each kind of growth. So you can see here that this is very similar to what we did before. The first difference is instead of starting with 1, we're starting with 5. So this starts at 5. And we're also using different letters. So t is equal to the time in hours, and f of t, the number of bacteria in millions. So we're already starting with 5 million. Part A says the number of bacteria increases by 5 million every hour. So if it increases, that means adding. So we're going to add 5, so this would be 10, add another 5, 15, add another 5, 20. That looks like our linear function, doesn't it? So they want us to find a formula. We know how to do that. That's the f of t equals the mx plus b. So in this case would be a t. So the m looks like it's a 5. And it also starts with a 5. Make sure it works. 1 is 10, 2 is 15, 3 is 20. Okay, let's do the same thing now with our exponential function. This is the new thing, exponential. So here we're going to find the number of bacteria doubling every hour instead of increasing. So there's the idea there. So we're still going to start with 5, but now we're going to double. So if we double, that's multiplied by 2. So this would be times 2 would be 10. Double again times 2 would be 20. Double again times 2 would be 40. So how did I get this? I got this 5 times 2, and then I realize it's 10 times 2, but I want to use these numbers. So this would be 5 times 2 times another 2. So I'll call it 2 squared. And then this one is going to be 5 times this guy times another 2. So it would be like 2 cubed. So there would be like a little 1 right there. So if I think of the formula for that, our f of t is going to be 5 times 2, it looks like. And notice when this is a 1, this is a 1. When this is a 2, the exponent is a 2. The exponent is changing. So that's what it becomes. You can check it. Plug in a 1, plug in a 2, even plug in a 0. Let's check that. 5 times 2 to the 0. We know 2 to the 0 is 1, so it does work. So if you skip example 2 just for a second, and we go back down to the end here, you'll see the definition. A function is exponential if it can be written in this form, a times b to the t, where a and b are constants, and the b has to be bigger than 0. F of 0 equals If you plug in a 0 here, b to the 0 is 1, so it's equal to a. And a is called the initial value. Every time t increases by 1, the output is multiplied by another factor of b. So b is called the factor. So now let's go back to example 2. An investor buys $1,000 worth of a risky stock and gets very lucky because the value grows quickly. Fill in the table and write a formula for V of t, the value of the stock after 2 years, assuming each type of growth. So first, let's define our variables. So let's let t be the time, it says t years, in years, and V of t be the value of the stock. And I'll just add in dollars. So at 0, what do we start with? We started with $1,000. So we're increased 2,000 every year. So we're going to add 2,000. So this would be 3,000. Add another 2,000. Add another 2,000. That would be the table. Again, the formula is that it has to be linear because we're adding. That's our old. So this would be the M is the rate, the 2,000. And then the initial amount is usually the B. And we can test it. 0 is 1,000, 1 is 3,000, 2 is 4,000 plus 1,000. It looks like it works. So that again is linear. Now let's look at exponential. Instead of doubling, the value of the stock now triples every year. That's still by a factor. Tripling means multiply by 3. So we're still going to start with 1,000. Now we're going to multiply by 3 to get 3,000. Multiply by 3 to get 9,000. Multiply by 3. Again, how do we get those? You can actually just do it here. Let's just go ahead and do that. So we know Q. Oh, let's not call it Q. Let's call it V of t. You can call the Q, or you can call it Q, the quantity, if you wanted. Why not? Is equal to A. If you remember, A was the initial amount. So the initial amount was 1,000 times B. B was the factor. The factor was the 3. It triples to the t. You don't have to put the parentheses in there. You could have let it be that, or you could have said, just don't make sure you multiply, because you always have to, if you know, like when x is 2, or t is 2, you know you have to do the exponent first. So you cannot multiply before you do the exponent. So that's why I like to always put in parentheses. And you can see that makes sense, because if you plug in a 1 here, that would be 1,000 times 3. If I plug in a 2 here, that would be 1,000 times 3 squared, multiplying by another 3. And if you multiply by another 3, or put a 3 there, that would be 1,000 times 3 cubed, which would be multiplying by another 3. So that is the formula for part B, our new exponential. So you can do it by logic, or you can do it with this new formula. So look at how much more an exponential grows. That is $27,000 versus only $7,000. So after 3 years, a linear stock would only make $7,000, where a exponential stock, right, would make $27,000. And by the way, this is when you're adding $2,000 every year. And here you're only multiplying by 3. So you think, that's not as good. But multiplication is always better. By the way, that's kind of what's going on with the COVID-19 in real life, isn't it? It's growing exponentially. So that's a prime example of exponential growth, kind of like the bacteria problem that we had up here.